Good evening. I hope I'm audible and my screen is also visible. And so this is uh, officially, this is not officially, this is 12th tutorial. So this is supposed to be the last tutorial, but there is an announcement that I should first do. That is that there will be an additional tutorial on the Monday, 13th of April from 7 p.m. to 8 p.m. There I will discuss whatever, mostly from the last section of this course. I will try to discuss the problems which is mostly from the last um, portion of the course, mostly linear product space and diagonalizability. And and if you have any other problem, you can share me. So that is on this mail ID. So I'm once again writing the mail ID here, and as well as if you have any other doubt. So that will be the last tutorial, 13th April, Monday, from 7 p.m. to 8 p.m. That will be the last tutorial for this course. My email ID is ma21d01a.smail.iitm.ac.in. I hope I'm getting correctly. So this is the mail ID. If you have any other doubt regarding this course, you can let me know. Any questions, you can let me know, because that will be the last tutorial. I will try to discuss those problems in the 13th April tutorial. So so let's start today's tutorial. So today's tutorial is, this is 12th tutorial, and please let me know if my voice is not clear, or is there any issue with my internet or anything visibility of screen. You can let me know. I'll try to fix that. So let's start today's tutorial. So this is tutorial 12. So as the previous tutorial, today is also I'll start with some problems, and according to that problem, I'll try to solve that. I'll try to introduce whatever is. I'll try to according to those problems, I'll try to discuss whatever the extra theorems or extra arguments is needed. So let's start with the problem, and let's see what it says. And okay. So what it is given, let V equals to C3 be an inner product space over the field complex number and equipped with the standard inner product. We know what is the standard inner product in V is equals to C3. Then standard inner product is just for any two element x, y, y1, z1 and x2, y2, z2. The inner product with x1, y1, z1 with x2, y2, z2, that is equals to summation of x1, no summation, then it will be like x1, x2 bar plus y1, y2 bar plus z1, z2 bar. This is the standard inner product. So uh, it is given that V is C3 with the inner product space equipped with the standard inner product on it, and let T be a normal operator on it. So what is normal operator? Recall that a bounded linear operator, not bounded. Recall that an operator, linear operator, a linear operator T on a finite dimensional inner product space is normal if T star T is equals to T star. Where T star is adjoint of T. Okay. So suppose that alpha belongs to V be a non-zero vector such that T minus 2I identity, I is here iota means square root of minus 1, and identity alpha is equals to 0, where I is the identity operator and T star denotes the corresponding adjoint of the T. Then which of the following statement is or are correct? So what are the options it is given? So already given that, what is given? Given that there exists a non-zero vector alpha, I think non-zero is mentioned here. There exists a non-zero vector alpha in V such that t minus 2I times 2I alpha is equals to 0. Okay. And then which of the following statement is or are correct? So here are the statement that t star minus I t star minus 2I alpha is equals to 0, t star plus 2I alpha is equals to 0, t star minus 2I alpha star is equals to 0, but alpha star is the complex conjugate of alpha. So, and t star plus 2I alpha star, here alpha star is the complex conjugate of alpha. These are the options. So there is a very standard theorem which is directly will give you this one, but I will straight and try to prove because that is very easy. So that's why I will try to prove that also. So there is in fact I can just mention that. So here is one point I just want to answer. These two options need not be, these two options are not necessarily correct. I mean these two options are not correct. Here I have to find the what is the correct options. Okay. So here alpha is complex conjugate of alpha star. So here given that alpha star is complex conjugate of alpha. Now what is alpha? Alpha is equals to some vector x1, y1, z1 in C3. This is what it is, the vector space. Now if I write alpha star, that will be complex conjugate. So that means, oh, this is just complex conjugate of alpha. Conjugate transpose. Okay. Alpha star is actually like x1 bar, y1 bar, z1 bar. This is what it is. But this is not going to do anything. Okay, let me state the theorem. So what is fact? It says already known fact. Let V be an finite dimensional inner product space, over a real field or complex field, that does not depend, and let T from V to V be a normal operator if 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 alpha is an eigenvector or characteristics vector, eigenvector of T corresponding to the eigenvalue C that is over the field, then alpha is, if and only, eigenvalue of C, if and only alpha is a characteristics, okay, then alpha is an eigenvalue of T corresponding to the eigenvalue C, if and only uh, if and only alpha is eigenvector of T star, the adjoint, corresponding to the eigenvector, sorry, it corresponds to the eigenvalue C bar. So what it says, that is, if T minus, or if T is equals to, if that is what it says, T of alpha is equals to C alpha, if and only if T star alpha is equals to C bar alpha. This is what it is saying. Okay. So with this, we already given that. So okay. So with this, we can clearly say here it is giving that 2I. Here, if I consider C is equals to 2I, then it is given that T minus 2I times. So this gives that T alpha is equals to 2I times alpha. Now, according to this theorem, T alpha is equals to C alpha if and only if T star alpha is equals to C bar alpha. So this, if and only if T star alpha is equals to 2I bar alpha. But what is 2I bar? 2I bar, I is the square root of minus 1, right? So conjugate of I is actually minus I. So this will be minus 2I alpha. So that will be like T star plus 2I times identity whole alpha is equals to 0. So that way, this is the correct options. This is of course not necessarily correct option. This is not correct option because it is given that T alpha is equals to C times alpha if and only T star alpha is equals to C bar times alpha. So that means this first one is not going to true. Second one is correct, but third one and fourth one, that is also not correct. You can just give an example that you can consider T is equals to 2I times identity operator and alpha is the vector. Alpha is the vector 1 0 0. Not 1 0 0 is not going to work. So according to this theorem, if it is given that P alpha is equals to 2y times alpha, it is given, then according to this theorem, T star alpha is equals to 2y bar alpha, so which is I have written that 2y minus alpha, right? So, so this is the first option. Second option is the correct option, and all other options are incorrect. I mean, how to get the other last two option was given that T star minus 2y times identity whole alpha star is equals to what it is, right? It is given. So here we can do one thing. If we consider T is equals to 2y times identity operator, if you consider T is equals to 2y times identity operator, then you can get that 2 T star is equals to 2y bar and alpha is equals to. So what about this? Okay. So what I will do, let's take alpha is equals to some vector like 1 plus identity iota 0 comma 0. This is the vector. Then and t is equals to, given that, okay, so let me phrase these questions properly. Given that t is equals to t alpha is equals to 2y times alpha, it is given. So what about t star alpha minus 2y t star alpha star? Here alpha star is actually just conjugate. If alpha star is equals to x1 bar, x2, x1 bar, y1 bar, z1 bar, whenever alpha is equals to just x1, y1, z1. Okay. So now question is what about this? Okay. So now here if we consider t is equals to 2y times identity operator, identity over C3, then clearly T alpha is equals to 2y times alpha, because T just T is, yeah, T is 2y times identity, then it will be clearly T alpha is equals to C 2y times alpha. There is no problem. Okay. But if I consider here what is T star? T star is actually 2y bar identity operator, that is equals to minus 2i into identity. Okay. Now T star minus 2i times identity. What is this minus 2i times identity? Minus 2i times identity, that is equals to minus 4i times identity. So now it is clear very much that this is of this operator with this alpha vector is not equals to going to be 0. Similarly, we can check, also one can check that t star plus 2i times identity whole alpha for these settings is not going to be, no, this is, in this case this is going to be 0 also. So we have to give the some separate operator. So what about we have counter, so that means option C is incorrect. I, I have tried to give in an counter example basically. Okay. So and for option D, what is option D says that what about T star plus 2y times identity alpha is equals to, what about this? Okay. So now if I consider, so I can't take this operator right now. So if I consider, good evening. So here I need to give a counter example. Alpha star. Here alpha star is that one. Here I need to give a counter example. Okay. This is correct. Yeah. Here I have to give a counter example for this fact that if um, T star 2y times identity alpha star is equals to 0, where alpha star is the complex conjugate of alpha. If I take T star, T is equals to, I can take, that's not a problem. Okay. So First of all, this is incorrect that we have checked. Second one is correct that we have checked. Third one is incorrect that we have given the counter example. Now only the fourth one, and fourth one is incorrect. So let me try to construct the counter example. That's all I need to do. Alpha is a non-zero vector, and t star plus 2i times identity. If t is equals to, yeah, mm, how to give counter example here? If I consider the operator ti 0 0 0 minus 2i 0 0 0 0, this is the operator, for example, t is equals to, or matrix basically, then t minus 2i times identity, that will be equals to 2i minus 2i, that is 0 0 0, and this will be like 0 minus 2i minus 4i 0 0 0 0, and let's take alpha is equals to, given that already given that t minus 2i times identity whole alpha is equals to 0. So let's take alpha is equals to 0 1 1 0 1 1 0 1. Then we can look at carefully ti time 2 I times identity alpha, that is column vector, it will be applied as a column vector 1 0 1, that will be 0. Okay, now if I consider t star, that will be equals to, that will be equals to 2i minus 2i. Yeah, let's say what is t star? T star is equals to minus 2i 0 0 0 2i 0 0 0 0. This is the 2 t star. Now t star plus 2i times identity, what it is? It is uh, hmm, t star plus 2i times identity, that will be 4i. So I need to give something below. If I write 1 here, if I write 1 here, if I write 1 here, still that's not going to create any problem. If I write 0 0 1 0 1 0 1, that is going to be 1. Next is, so that's not becoming 0. So let's take alpha is equals to this one. Then if we multiply 0 0 1, then first column is, oh, so this one 1 0 0. So then if we write 1 0 0, so multiply it, this will be, first one will be 0, second one will be 0, third one will be 0. So this is clear. Now what is t star? T star, then this t star will become 1 here. So if you multiply alpha star is actually, alpha star actually, here it is, you can check this is correct. Now alpha star, that is equals to 1 0 0. So now if we use 1 0 0, what did happen? This will be like minus 2i times, okay, ti star is equals to this, okay, 1 0 0, this is equals to minus 2i times, this is what it is, next one will be 0, and last one will be 1. So this is of course not equals to 2i times, not equals to minus 2i times alpha. This is of course not equals to minus 2i times alpha. So this is counter example, you need to check it a little bit carefully. In fact, I can do it here also. T star plus 2i times identity, what it is right now? Right now it is 0 0 0 0 4i 0, and 1 0 and 2i. Okay, here it is minus 2i, but that is not going to do anything. So 2i. So if I multiply with 1 0 0, what it will be? It will be equals to 0 0. First one will be 0, second one will be 0, third one will be 1 0 1. So this is of course not is equals to 2i, not equals to 0. So it is supposed. So this is the second example it is asked. Okay, this is the fourth one option. So fourth option is also incorrect. So option D is also incorrect. So is it clear? I am just trying to, for the first two, this is true for the, from the, say, from this theorem it is following that for a linear product space, finite dimensional linear product space, if T be a operator, normal operator, And then if alpha is an eigenvector corresponding to an eigenvalue c for the linear operator t, then alpha again will be the eigenvector corresponding to the operator t star, and operator t star corresponding to the eigenvalue c bar. With this, first two option will be clear what it is. So this is what it is. Is it clear that I have tried to give the counter example for last two options, and for first two I have tried to use the theorem. Is it clear? I hope it is clear. If there is any doubt, you can let me know. I'll try to go back and once again try to explain. Okay. In fact, even if I am going to the next problem, you can try to pause me and try to ask me the problem. So this is the another problem. So what this problem says, give a finite dimensional linear product space, give a finite dimensional linear product space V over C, T be a linear operator on it, W be a subspace V, which is invariant under T, and alpha belongs to W and beta belongs to W bar. W par. What is W par that I am going to discuss? Then which of the following statements are incorrect? Here I have to find incorrect. So for let, this is for any inner product space, let V be an inner product space, W subset of V be in subspace, be a subspace of V, then W par is equals to all those vector alpha belongs to B. That is called W par. All those vector alpha belongs to V such that alpha with inner product beta is equals to 0 for all beta in W. This is called orthogonal complement actually in V. So all those vectors which orthogonal to every vector in W. This is what it is. Alpha, an element alpha from in V that will be inside W par, if that is orthogonal, that inner product with that vector to the every vector of W is actually 0, then that is what is called W par. This is what it is, W par. I hope its definition is clear. This is called orthogonal complement. Complement of W in V. Okay. Now what is the question? This says that that W also, it is here, it is given that W is an invariant subspace of T. Invariant subspace of the linear operator T from V to V. That is, if we take TW subset of TW is actually subset of W, and this fact is same with that for every for all beta in W, T beta is again in W. This is what it is. Okay, this is what it is called the invariant. Now here what I will prove actually, here what I need to check, if alpha is coming from W and beta is coming from W par, then some condition as it is given I have to check. So let's take, if alpha is coming from W and beta is coming from W par, then T alpha beta. Okay, what we can say about that? So note that here T alpha is again in W and beta is in W par. So by definition of W par, if I consider an element coming from beta, coming from W, that will be orthogonal, that will be inner product with any vector. So basically W and W par is something like that. If you take alpha from here, beta from here, and take the inner product, that will be 0. Okay. So now here T alpha is in W and beta is in W par, then that has to be 0. So that means as a option, this is incorrect, but this is as a statement correct. And similarly, if I write alpha and T beta, what I can say about this? Here it is given that alpha is in W and beta is in W par, and we are given that W is invariant under T. That means T alpha is again in W, but W par is not necessarily invariant under T. So what I can say about this, but I'll go to little later. But let's check other options too. Note that. Okay. Once I know this fact that T alpha is equals to 0, and then we know this T alpha is actually equals to alpha T star beta, right? Okay. T alpha is equals to alpha T star beta, because that is the adjoint property due to the property of adjoint. Okay, so this is what it will happen, because we know that adjoint of a linear operator is defined like this way. So therefore the last option is also as a option incorrect, but as a statement this is correct. As a statement correct, but option as a option incorrect, because T alpha beta is same with alpha T star beta. This is how adjoint is defined for any vector. For any two vector alpha beta coming from the operator space V, T is a linear operator from V to V. The T star is something like that. T alpha beta is equals to alpha T star beta. This is what it is, the inner product adjoint of a linear operator T, defined like this way. Now my point is that, so these two options, now look at these two options carefully. These two options actually saying the same thing. Alpha, then this way alpha T beta, that has to be equals to T star alpha comma beta. This is true for any alpha beta in the vector space V. In particularly whether alpha is in V W and beta is in W part, that doesn't matter. This will be true always. Okay. Whether alpha is in coming from W and beta is coming from W part, that doesn't matter. Alpha inner product T beta, that has to be equals to T star alpha inner product beta. So if one is 0, then other has to be 0. Okay. So that means there, from here you can directly say that okay, these two options are exactly I mean, these two options are not correct. These two can't be. Okay. So my point is that if one is true, other will be true. One is false, the other will be false. So that means from here you can say that as a option they are incorrect, as a statement they are incorrect, but as a option correct. But because there you have to get only one incorrect options, that you have to find. But okay, let me give you the why that can happen. I mean, if W is invariant subspace, then why inner product T alpha beta, that need not be 0. This is what I want to say, right? So I have to give an inner linear operator T, and then something that, let's take an inner product. Let's take an inner product in R3, and the linear operator T actually sending. Let's take consider V is equals to C3. Okay, and let's take, we know that 1 0 0 0 1 0 and 0 0 1, this is what it is, the linear operator. Okay, this is what it is, the basis, orthonormal basis. Actually this is standard orthonormal basis of the vector space V over C. Let's take T be the linear operator from V to V. What it is, that mapping x y z to x 0 comma 0. Then clearly if W is actually, if W is equals to span of 1 0 0, then T of 1 0 0, that will be 1 0 0, and any vector which is in linear in spanning set of 1 0 0, that will map to the first, that will map to the W. That means W is invariant under T. Okay. Now question is, what is orthogonal complement of this? That will be clearly, you can check span of 0 1 0 0 0 1. Okay, then you can clearly, this you can check. I am just writing, this is to for check. You can check, even if you want to check me here, then I can check also. That's not a big deal, that why W part of 1 0, when W is this one, why W part is going to be that. I can check very easily, but this is orthonormal basis, you can guess at least. Okay, so now point is that I want to prove that if I take a vector from there, I want to get the inner product with T x y z. Okay, let's take 1 comma 1 comma 1, that's coming from the vector space V. Okay, but I need that element coming from the vector space W, and I need something like alpha is coming from W and beta is coming from W parp, and T alpha, what it is giving, that alpha T beta is not equals to 0. Alpha T beta is not equals to 0. This is what I want to give. I mean, there exists an alpha such that, and beta like this way, such that alpha T beta is not going to be 0. T just projection I am taking. So then if I take alpha is equals to 1 0 0 and beta is equals to, no, I can write this one, spanning set of 1 1 0 1 0. This is also spanning. You can check that W perp is actually span of this. Span of this it will happen. There is no problem. Span of this will happen. So now then alpha we have to find alpha beta such that this, okay. So let me find alpha. Alpha is, let's take 1 0 0. There is no problem to taking 1 0 0 0, and beta is actually equals to take 1 comma 1 comma 0. Then this is in W, this is in W part. Okay, now let's take inner product 1 comma 0 comma 0 with t of 1 comma 1 comma 0. So t actually mapping the first element to the, I mean to the first coordinate, and all other coordinate to sending to 0. So 1 comma 0 comma 0, then it will be 1 comma 0 comma 0, and this is the standard inner product 1, which is not equals to 0. That means we can find an vector alpha coming from V, beta coming from W, such that W bar alpha coming from W and beta coming from W part, such that alpha inner product T beta is not going to be 0. Okay. So that's why one option is incorrect, so other option, I mean one statement is incorrect, then other statement automatically incorrect. Is it clear? If there is doubt, you can let me know. These are not very, I mean, you can explain it once again, try to be. Is it clear? Okay. So yeah. So I'm going to the next problem. If there is any doubt, you can let me know. Even I'm going to the, when I'm discussing the next problem, that time also. Consider a matrix. This is given A, B, C, D. Okay, where A, B, C, D are distinct complex number. Here it is distinct given. Okay, and B not equals to 0. That is also given. B not equals to 0, purely imaginary. So what is purely imaginary? Purely imaginary means, I think, without no real part will be there. Okay, let me check whether. Okay, then the matrix A is normal if and only what happens. So let A is equals to A, B, C, D, B, D. Okay, A, B, B, D. So you can look at carefully. This is actually symmetric matrix, but symmetric does not going to do anything here. But this is symmetric. This is observation, you can say. Now what is A star? A star is actually conjugate transpose. So we have to take conjugate and we have to take transpose. But here it is symmetric, so transpose is not going to do anything. So if A is normal, then we should have A star. So that means A bar, B bar, B bar, D bar, A, B, B, D. This is what it is, A star A. That has to be what we have to, we should get that A, B, B, D, A bar, B bar, B bar, D bar. So what we should get that mod of A square plus mod of B square. This will be A bar B plus B bar D, and this would happen B bar A plus D bar B, and this should happen then mod of B square plus mod of B square. This should be equals to mod of A square plus mod of B square. This will be like A B bar plus B D bar, and this will be like B A bar plus D B bar, and this is like mod B square plus mod B square. So that means these two terms are automatically satisfying. Whatever B or A you choose, that these terms are automatically satisfied. Whatever B or A you choose, that doesn't matter. Okay, the only fact is that is we should have, or this is if and only, that A B bar plus B D bar, that has to be equals to A bar B plus B bar D. This is what we should get. Okay, but then what are the options we have here? So let me look at. So what are the options? A plus D purely real, A plus D purely imaginary, A minus D purely real, A minus D purely imaginary. These are the options. So actually we have to check what is A plus D and A minus D. This is what we have to check. Okay. Now here it is given that here it is given that B is purely imaginary. Given that B is purely imaginary, that is, I hope I'm writing correct, B is equals to some I into x, for x is in real number and that not equal x greater than 0. Not greater than x not equals to 0, that we need at least, okay? So now what we can say, B bar is equals to minus ix, we can write, okay? Then what will happen, A B bar, this one will give me that A minus ix, I times ax, that is B bar, plus B D bar, that will be equals to, there is no condition over D, right? A and D distinct complex number, they are distinct complex number, and B not equals to 0, purely imaginary. This is equals to I A bar x plus B bar is equals to minus 2 minus A I x, B bar is equals to minus iota x, I A x D. X is actually real number, okay? A bar B, B I have not replaced here, no, sorry. B I have to replaced. So just replace B and B bar in the this above, this one. So what will happen? Minus I ax, B bar is ix. So B bar is minus ix. Okay, B bar is minus x. If I replace this, minus I ax plus B is ix. This will be plus I D bar x, which is equals to A bar. A bar is actually equals to A bar and B is actually ix plus B bar. B bar is actually minus I dx. This is what we have. So now if I take these two in this side, I mean just I can write I ax plus I dx. This is equals to I a bar x plus I d bar x. So x is non-zero. So x we can do cancellation. I is also we can do cancel. So minus a plus d, that is equals to, we have a bar plus d bar. I also have cancelled, and I think I have written one wrong sign here. So that means we can write here it is also minus. So that means what we can get here from, we can get here is that a minus d bar, I think a minus d is equals to d bar minus a bar, that is equals to d minus a bar. Okay. So what happens when this type of things happens? A and D are distinct. Given that A and D are distinct, given that A and D are distinct, that means A minus D is equals to, or I can write this one as the minus of bar. So A minus D is actually not equals to 0. When this type of situation can happen, that if I take a complex number x which is non-zero, that is x is equals to minus x bar. When this type of situation happens, whenever x is completely purely a complex number, if x is a z is a complex number such that for which we have z is equals to minus z bar, then z has to be purely real number, purely imaginary. Why? I can let you know. Suppose z is equals to, for any complex number z which is equals to x plus iy, if z is equals to minus z bar, that implies that x plus iy is equals to minus of x plus iy its bar, that is equals to minus x minus iy bar, that is equals to minus x plus iy bar iy, right? X and y are real, so that force you that will force you that 2x is equals to 0, that will force you that x is equals to 0. That means z is purely imaginary. Okay, so this is what it is saying, that from here you can say that a minus d is purely imaginary. So, and whatever I have done here, that completely reversible. So that means this is if and only. So basically, so that is A is normal if and only A minus D is purely imaginary. Okay. So that means A minus D is purely imaginary. This is the last option is correct. So all other options has to be incorrect automatically. Okay. So is it clear? This is very simple. I believe this is very simple, but every point, whatever is given here, like A and D are distinct real numbers. This is also using B not equals to 0 purely imaginary. That is also, every fact has been used here, whatever it is there. Okay. So I'm going to next problem. If there is any doubt, you can let me know. I'll try to explain it once again. Even I'm going to the next problem, that time you also stop me and ask me the problem. Okay. Okay. So let me go to the next problem. So let's see what this problem says. Um, Given a sesqui-linear form F on linear product space V, equipped with the standard inner product on it, f x1 y1 z1 x2 y2 z2 is equals to this. What this some inner product is given. Okay, this is not the inner product, actually sesqui-linear form. So what is sesqui-linear form? Let V be an inner product space. Okay, then a map f from V times V to whatever the field f is said to be sesqui-linear form if f of alpha c alpha plus beta comma gamma is equals to c of f of alpha comma gamma plus f of beta comma gamma, and f of for all alpha beta gamma coming from the vector space V and c coming from the field wherever it is vector space defined. And this is the linearity in the first component called. Another is that alpha comma c beta plus gamma is equals to c bar f of alpha beta plus f of alpha gamma. Okay, this is called the conjugate linearity or sesqui-linearity. Linearity on the second, conjugate linearity on the second variable is called sesqui-linearity. Conjugate linearity in the second variable. Okay, so now the point is that this is what is called by sesqui-linear form. But if the vector space V is over real, then this sesqui-linear form on inner product space V is equals to R3, that doesn't matter. That's actually the bilinear. Linear in the first and linear in the second. Because here V is the vector space R3, and I believe here it is considered the vector inner product is over the real field itself. Okay. So what is given the as inner product, what is given, that f of okay, let me write the inner product x1 y1 z1 comma x2 y2 z2. This is given is equals to this is given equals to 2x1 x2 plus 4x1 y2 minus 3y1 y2 plus 2y1 z2 plus z1 x2 3z1 z2. Okay, this is where it is given. So what are the question asked? The linear transformation T induced by F is given by. This is good questions. So okay, I should not have written this. Then let me write a theorem here. Actually, the theorem says if we have a bilinear form, sorry, sesquilinear form, then there should be corresponds a linear operator. So theorem says, just let me try to find the exact notation, exact statement that can be proved, but I will not prove. I'll not prove, and I'll just let you know. So if you think that theorems is need to be proved, then I can prove, but you have to ask them that should I then I will prove. Otherwise, I'm just going to state the theorem and use that as a to prove the result. So fact that or theorem says that if V be an inner product space, okay, finite dimensional inner product space, finite dimensional is needed. V be an finite dimensional, V be a finite dimensional inner product space. Let F from V times V to the field F is an sesqui-linear form. Then this finite dimensional thing will help you to find the operator. Then there exists a linear operator V to V such that f of alpha beta is equals to T alpha inner product T beta. This should happen for all alpha beta coming from the vector space V. I am not proving this right now. If you think I should prove, then you can ask me, I'll try to prove, but right now I'm avoiding to prove and use this as a theorem. So I don't use that, I don't, but I'm just trying to say that, okay, I don't need how the T actually appears here, but okay, I will try to obtain that, okay. So that means this is giving the existence of operator T, but that means that is f of given that x1 y1 z1 and x2 y2 z2, that has to be equals to, this is given that this is equals to this is equals to 2 times x1 x2 plus 4 times x1 y2 minus 3 times y1 y2 plus 2 times y1 z2. I hope I'm writing correctly. Z1 x2 plus 3 times z1 z2. Let me check whether because this is, if this is wrong, then everything going to be wrong. 2x1 x2 plus 4x1 y2 and minus 3 4x1 y2 minus 3 y1 y2 plus 2 y1 z2 plus z1 x2 plus 3 z1 z2, and that has to be equals to T of x1 y1 z1 comma x2 y2 z2. Okay, this has to be okay, and this has to be true for every x1 y1 z1 comma x2 y2 z2 whenever it is coming from the space R3, it is given R3. Okay, now my point is that I have to find T x1 x2 x3, right? We want T x1 y1 z1 what it is. Okay, so let me obtain T of 1 comma 0 comma 0. I want to obtain this. So what is this? So if x1 y1 z1 is equals to 1 comma 0 comma 0, then what I'll obtain T of 1 comma 0 comma 0 with inner product x2 y2 z2. This has to be equals to, replace x1 is equals to 1 and x2 y2 x1 equals to 1 and y1 and y2, that has to be 0. So in that way, if I replace x1 is 1 and y1 z1 is 0, then what I'll have, y1 z1 0. So this is going to be 0, this is going to be 0, this is going to be 0. Okay, so that means I will obtain x1 is 1, so that means I will obtain 2x2 plus x1 is 1 4y2 plus 2y1 z2. Okay, no, sorry, y1 is 0, right? Y1 z1 both are 0, so this is also going to be y1 z1 z1 y1. Okay, everything is going to be 0, this is also going to be 0. So basically I have this one, right? Now if I want to make it as an inner product, what I can write, we can easily say that 2 comma 4 comma 0 inner product with x2 y2 z2. We can write this one, and this is true for every x2 y2 z2. This is true for every x2 y2 z2, and that gives me that this gives me that t of 1 comma 0 comma 0 is equals to 2 comma 4 comma 0. Similarly, if I want to obtain t 0 comma 0 comma 1 comma 0 and x2 y2 z2, then I have to replace x1 is 0 and y2 x1 is 0 and z2 is 0, z1 is 0. So x1 0 means this is going to be 0, z1 0 means this is going to be 0, and z1 0 means this is going to be 0, and x1 0 means this is going to be 0. So we have only minus 3y1 y2 plus 2y1 z2, but what we know, y1 is equals to 1, so 3y2 plus 2z2, and this can be written as we have x y2 z2, we will have this is 0 minus 3 2 inner product with x2 y2 z2, and this is also true for every x2 y2 z2. So this is going to give you that 0 comma 1 comma 0 is equals to 0 minus 3 comma 2. Similarly, if one try to obtain 0 0 comma 1 with x2 y2 z2, and here we have to replace x1 and y1 0. Okay, so x1 y1 0 means this is going to be vanish, 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 and this last will appear only. Z1 x2 plus 3 z1 z2, but z1 is equals to 1, so basically this will be equals to x2 plus 3 z2. So then you can write it as 1 0 3 inner product x2 y2 z2. So this is what we obtained. So this is what we obtained. So this is going to give you that t 0 comma 0 comma 1 is nothing but 1 comma 0 comma 3. So once you have all these things, that there is three things. One is this one, another is this one, another is this one. Now suppose I want to obtain x comma y comma z. Just let x comma y comma z, and we know that x comma y comma z can be written x of 1 comma 0 comma 0 plus y of 0 comma 1 comma 0 plus z of 0 comma 0 comma 1, and t is a linear operator. So using the linearity, what will obtain x of 1, t is sending 1 0 0 to 2 comma 4 comma 0, t is sending 0 1 0 to 0 minus 3 comma 2, t is sending 0 0 1 to 1 comma 0 comma 3, that is going to be like 2x plus z comma 4x minus 3y comma 2y plus 3z. 2x plus z, 4x minus 3y. Let me this is problem number 4. 2x plus z, 4x minus 3y, 2y plus 3z, and that is option A. 2x plus z, 4x minus 3y, 2y plus z. That you can look at carefully. I think this is okay. This is not able to okay. So this is the correct options. All other options are automatically incorrect because that is completely I'm trying to obtain. Okay, 2x plus z. So that will give me the correct options. So is it clear? Is it okay that is there any doubt in this, specifically this problem, that any argument or any computational way, is there any doubt? If there is any doubt, please let me know. Okay, so I hope it is clear. If there is any doubt still, you can let me know and I will try to explain it once again. Not a problem. So let's go into the next problem. I think this was problem number 4. Okay, this is 5. So what this problem says, giving a linear operator t, this is the operator it is given, that t of x y is going to be ax plus b, cx plus dy, her abcd are complex number on the standard inner product space C2. Then corresponding sesqui-linear form. Okay, this is very easy. So what is the sesqui-linear form? If you remember the last time, what one theorem I have said, if you have a sesqui-linear form f from v cross v to v, then there exists a linear operator t from v to v such that f of alpha beta is equals to inner product of t alpha beta for all alpha beta belongs to v. On the other hand, it is known, it is clear, okay, let v be an inner product space, let v be an inner product space over some field f, let t be a linear operator from v to v be a linear operator, then a map f from v cross v to the field f defined by f of t of alpha comma beta is actually is a sesqui-linear form. This you can check. Sesqui-linear means it is linear in the first component, and why this is linear in first component? Because t is linear in first component. And why it is linear in second component? Because the inner product on the second component, here it is t is linear in the first component and inner product is linear in the first component. And why it is anti-linear in the second component or conjugate linear in the second component? Because inner product is conjugate linear in the second component. Okay, that is the reason. I hope if you ask still I can prove that I can sesqui-linear form. So this is what it is in general. If you have a inner product space V and if you have a linear operator T, if you define a map f from v cross v to f by given by this way, that alpha beta is equals to t alpha beta for all alpha beta belongs to the vector space this, then this is an sesqui-linear form. Okay, that is sesqui-linear form means that c alpha plus beta comma gamma is equals to c of f alpha comma gamma plus f beta comma gamma, and anti-linearity, that is alpha comma c beta plus gamma is equals to c bar f of alpha comma beta plus f of alpha comma gamma. This is the trivial part. Non-trivial part is the previous theorem which I have used, that if you have a bilinear form, then that will be actually coming from a linear operator t. This is what it is. Okay. Now we have to find the this what it is. Okay, this form. So let's then what, this is very easy right now. I hope x1 y1 comma x2 y2. This is I have to find that has to be equals to inner product of t x1 y1 with x2 y2. And what is the inner product of what is tx1 x2? Tx1 x2 txy equals to ax plus by cx plus dy. So this will be like ax1 plus by1 comma cx1 plus dy1. I hope this is what it is given, ax plus by cx plus dy. This with inner product with x2 y2. So if we take the usual inner product, it will be like ax1 plus b1. This is real inner product or complex inner product. So this will be with x2 bar plus cx1 y2 bar. So this can be written in simplified form, ax1 plus x2 bar by1 plus x2 bar plus cx1 plus y2 bar plus dy1 y2 bar. Okay, so this is going to be ax1 x2 bar. If you look at carefully, this is matching only with ax1 x2 bar by1 y2 bar cy1 x2 bar cx1 ax1 x2 bar, this is what it is, by1 x2 bar, this is what it is, cx1 y2 bar, this is what it is, and dy1 y2 bar, this is what it is, and all other thing automatically will be incorrect because you can check that is not matching at least one place. So this is the correct options, all other options are incorrect then. Is it clear? I hope it is clear. So if you have any doubt, you can let me know. This is just usual linear product I am using. So let me go to the next problem then. This is done. Okay, so what this problem says, which of the following statement is or are incorrect for a linear operator in a transformation T defined on a finite dimensional inner product space V. There always exist an orthonormal basis. Okay, so what it says, which of the following statement is or are incorrect for a linear transformation T defined on a finite dimensional inner product space. Finite dimensional inner product space and a linear operator T. There exists an orthonormal basis of V such that I'll write this as a beta. Such that the matrix representation of T is an upper triangular matrix. Okay. Another is that which of the following statement is or are incorrect for a linear transformation T defined on a finite dimensional linear product space V. There always exists an orthonormal basis of V such that the matrix representation of T is an upper triangular matrix. Another is that the matrix representation of a normal operator is always diagonal. Another third is that if the of matrix representation A of T with respect to some orthonormal basis is diagonal matrix, then A is normal. Another is that the eigenvalues of a normal operators are real. Who who is or are incorrect. So here is actually many options are incorrect. Here only one option is correct, and that is the third option. Why this is? First option what it says that there always exists an orthonormal basis of V such that the matrix representation of T is an upper triangular matrix. Let me recall one very old theorem which we have already used when I am not going to the inner product space that time. So that fact I can say, if V be an finite dimensional inner product space, finite dimensional inner product space or vector space over field F, then the matrix representation of T, then there exists an field over F, and F is, the field is actually algebraically closed. Like you can consider the complex field, algebraically closed. Then there exists a order basis. Then there exists an ordered basis of V such that matrix representation of T with respect to this basis is upper triangular. So basically what I am saying, if you don't have the complex field, then there is no guarantee that the matrix will be upper triangular. I mean, there will exist a matrix representation upper triangular. For example, you can consider the matrix representation, you can consider this matrix. Let's take, let A is equals to 0, -1, 1, 0. So then this is not upper triangular. Because why this is not upper triangular? Let me show you why this is not. Let A be a matrix over the real field, be a matrix over the field R. Okay. Then my point is that A is not upper triangular. I mean, there is no basis such that you can make you can change to an upper triangular matrix. Why it is not possible? If you consider the characteristics polynomial of A, then it will be like determinant of A minus xi. That will be like x minus x minus 1, 1 minus x. Okay. This is what it is. Determinant of this, and this is equals to x square plus 1. Now, there is no root of this polynomial. There is no root in R of the polynomial x square plus 1. But this polynomial has root in complex field, and they are iota and minus iota. Yes. I mean square root of minus 1 and minus of minus square root of minus 1. But the point is that here is no eigenvalue. So if it does not have any eigenvalue in real field, then if it is possible to be upper triangular, then upper triangular entries has to be real. Okay. but that those terms are actually the eigenvalue, but here it is not the case. Okay, I mean, if it is upper triangular, that means there exists an basis. We can change the matrix with respect to which, by I mean, there is an invertible operator A such that A will be equals to P inverse AP is equals to actually upper triangular matrix. But if we convert a matrix A by this P inverse P, then we know eigenvalues will keep as it is. Eigenvalues will be same because the characteristics polynomial has to be same, so eigenvalue has to be same. But if it is upper triangular over real field, then upper triangular entries, main diagonal entries has to be real. So once the main diagonal entries is real, those main diagonal entries is supposed to be the eigenvalue of the matrix A, because consider, we know that eigenvalue of A and P inverse AP are same. Whatever invertible matrix you choose, that doesn't matter, are same. Now, if we change the basis, that means you are converting A to P inverse AP for some suitable matrix P, invertible matrix. Now, if there is an invertible matrix P such that P inverse AP is upper triangular matrix, that means the main diagonal entries, which is supposed to be real, they supposed to be the eigenvalue of the matrix A. But if their eigenvalue, they has to be real. But we are seeing that the eigenvalue of the matrix, there is no real eigenvalue of the matrix A. So that's why the first statement is actually incorrect. Okay, there always exists an orthonormal basis of V such that the matrix representation of T is an upper triangular matrix. That statement is incorrect. So there's an option, it is correct. Another is the matrix representation of a normal operator is always diagonal. There is a theorem. Theorem says that the matrix representation, there exists a theorem that is very standard and the ultimate theorem of the advanced linear algebra course, you can say. Ultimate means that is the one of the main target, whatever the things has been developed to go to, one of the main target, that to given if let V be a inner product space, T from V to V, be a finite dimensional inner product space, be a finite dimensional inner product space, T from V to V, be a normal operator, be a PN operator, be a linear operator, then there exists an orthonormal basis of V such that the matrix representation of T, is diagonal, that is diagonalizable. This is what it is, diagonalizability, right? There exists an basis such that this will happen. Diagonal if and only if T is normal. If T is a normal operator, you will always able to find an orthonormal basis consisting eigenvectors. That means that T is diagonal. I mean, if you are able to find an orthonormal basis consisting eigenvectors, that means T is diagonal, and T is diagonal means there exists an orthonormal basis with this, I mean, consisting eigenvectors or diagonalizability. So T, that happens if and only if T is normal. Okay. So now, but that does not guarantee that you choose any order basis and try to give the matrix representation. That matrix representation is actually has to be diagonal. That is, there is no guarantee. You will have one choice at least. That does not assure you that any basis you choose you will get. For example, so that's why, but that does not guarantee you. But that does not guarantees that the matrix of a that the matrix representation of a normal operator is diagonal. We will have an basis with respect to the matrix representation is diagonal, but that does not imply that any basis you choose and the matrix representation of respect to that is diagonal. That's not the. For example, if we consider the A is equals to like the older one, minus 1, 1, 0, so we know the characteristics polynomial is actually x square plus 1. So let's now consider this is over C, complex field. Then eigenvalues are minus 1, minus I, and I. Okay, I is the square root of minus 1. So basically, characteristics polynomial will be x minus I, x plus I. So here we have two distinct roots. So that is A is diagonalizable, right? That means there exists a basis with respect to which the matrix representation of A is supposed to be minus I 0 0 I, right? But the matrix representation of A here it is that is not actually diagonal. That is actually, now if I consider T from C2 to C2 given by T of X is actually AX, considering X as the column vector in C2, then the matrix representation of T with respect to the standard orthonormal basis, that is nothing but 1001, is actually the matrix is A, but that is not diagonal. But A is not diagonal. So basically, I am trying to say that if you have a diagonal normal matrix, normal operator, you have a basis for which you will have a diagonal representation, but you will not diagonal matrix for any basis. Okay, so that's why the second option, as a option, it is correct, but as a statement, this is also false because I have to find the incorrect options. Third one is the if the matrix representation of A of T with respect to some orthonormal basis is diagonal matrix, then T is normal operator, and that is what it is exactly the theorem stating. There exists an orthonormal basis of B such that the matrix representation of T is diagonal, that if and only if T is normal. So that means that this is as a statement correct, but as an option this is incorrect. Last option is that the eigenvalues of normal operators are real. That is also as a statement correct, but as an option incorrect, because here A, here the operator T, here the operator T is normal. Why this is normal? Because T is diagonalizable. I mean, you can look at T is normal. You can check here. You can consider A and you can check T is normal. But its eigenvalues are square root of I and square root of minus I, and they are not real. They are not real. So basically, what we obtained that this is here it is asked that the eigenvalues of the normal operators are real. That did not need not necessarily. The matrix here it is given the operator T defined like this way, that is normal matrix, and operator is also normal operator, but the eigenvalues are not real. When it is real, whenever you have the linear operator is self-adjoint, in that case it is real. Okay. Self-adjoint is more stronger condition than normal. A self-adjoint operator is normal, but a normal operator need not be self-adjoint. Okay. So is this questions clear to everyone? Let me go to the next problem. Okay, so what is this problem says? Given an inner product V on R3, no, V is R3 actually, equipped with the standard inner product on R3. So it is completely on real field, and a linear operator T from V to B defined by this way. The resolution of identity operator given by. So I have to say what is resolution of identity operator. Resolution of identity actually the expression of identity in the three operators E1, E2, E3. They are orthogonal projection in some sense. Orthogonal projection in some sense. their sum has to be 0. I think I'm saying correctly. Okay, let me. E1, E2, E3. Then I has to be equals to E1 plus E2 plus E3. Okay. So what is the resolution of identity? So here let's take the standard order basis, that is equals to 1 comma 0 comma 0, 0 comma 1 comma 0, and 0 comma 0 comma 1. This is standard orthonormal basis. Standard orthonormal basis. Okay. Now standard orthonormal basis. Now what we can say is that that's the matrix representation of T with respect to this standard basis is actually, if you look at carefully, that will be 4 minus 1 minus 1 xyz minus 1 minus 1 4 minus 1 4 minus 1 minus 1. That's okay. 4 minus 1 minus 1 minus 1 minus 1 4 minus 1 4 minus 1. So clearly one of the eigenvalue is actually 2. That is the sum of rows and sum of columns. That is exactly same. But okay, let me. If T is diagonalizable, if T is diagonalizable, then and C1 C2, then let T is diagonalizable. Let T is diagonalizable. Then if C1 C2 C3 are, there can be 3 distinct eigenvalue maximum. C1 C2 C3 are distinct eigenvalues of the operator T. Then if I consider Wi is actually equals to eigenspace, that is the kernel of all those vectors x in C3 or R3, such that T minus C1I whole x is actually equals to 0. That is the eigenspace. Okay, eigenspace of Wi, eigenspace of Wi. Then projection, if EI is actually from V to Wi, be the orthogonal projection, then first we should have that W1 plus W2. These are the direct sum. They are distinct. Okay, direct sum is equals to V. Second, we should have the E1 plus operator as an E3 is has to be the identity operator, and third one is that the T operator can be written like C1 E1 C2 E2 plus C3 E3. Okay. So basically, if I can find W1, W2, W3, then we can also obtain E1, E2, E3. But the question is, what are the first of all eigenvalues? I need to know what are the eigenvalues. So let me write the matrix here. I don't know this matrix looks very. This is self-adjoint matrix as well. Minus 1, minus 1, 4, minus 1, 4, minus 1. So this is the matrix. So let's take x minus. This is actually going to be big. Problem is that. X0 0 0 x0 0 0 0 minus, I'm going to this one. This is going to be like x minus 4 plus 1 plus 1 0 minus 1 1 minus x minus minus 1 x plus 1, and next one going to be minus 4. Oh god. Now this one is going to be like 0 minus 1, 0 4 is minus 4, and oh, there it has to be x plus 1. Yeah, this is what it is. So I have to find the determinant of this. So determinant of the x minus ai, so xi minus a, that is equals to x minus 4 into x plus 1 square minus 16. This is the first thing, minus 1 corresponding to this entry. This gone. That will be x plus 1 minus 4, x plus 1 minus 4, and last one will be like 1, that is 1. It will be minus 4 minus x minus 1. Yeah. So this will be like x minus 4 x square plus 2x plus 1 minus 16 minus x, I hope I am doing correctly, minus 5 minus x. Okay, so this will be x plus 5, right? So this will be x plus 5. So this is going to be x minus 4 x square plus 2x minus 15. Okay, 5 3 breaking x plus 5, 2 times x plus 5. This is going to be x minus 4. This is going to be x square plus 5x minus 3x minus 15 minus 2x plus 5, and this is going to be like x minus 4, and this is going to be like x plus 5 x minus 3 minus 2x plus 5. So this is going to be like x plus 5 x minus 4 minus x3, that is going to be, oh, this is 2 is outside. 2 is outside, that is x square minus 7x plus 12 minus 2, that is equals to x plus 5 x square minus 7x plus 10, that is 5 2 breaking, x plus 5 x square minus 5x minus 2x plus 10. This is going to be x plus 5, and this is going to be like x minus 5 and x minus 2. So the eigenvalues are 2, 5, minus 5, distinct. So this is a linear operator on the three-dimensional space. So the characteristics polynomial is x minus 2, x minus 5, x plus 5. Then the minimal polynomial, there is no other option. Minimal polynomial this has to be like x minus 2, x minus 5, x plus 5. So minimal polynomial is actually product of distinct linear factors. That gives you that the linear operator T is diagonalizable. This is going to give you. Now we have to find the eigenspaces. This is very big problem. I'm wondering whether there is any easiest way, but I don't think there is an easiest way. Okay, no, there is an easiest way. So we have to find now T minus, we have all the eigenvalues like 2, 5, minus 5, right? So eigenvalues are 2, 5, minus 8 minus 2 times identity whole into x comma y comma z, that is equals to, I'm not going back to that, but let me, t x y z, what it is going to map, t x y z is going to map you that 4x minus y minus z minus x minus y plus 4z comma minus x plus 4y minus z minus 2 times x comma y comma z. So this is going to be like, if you delete 2x from the first component, that will be 2x minus y minus z comma minus x minus 3y 2y from the second component, 4z, and if I delete 2z from the last component, that will be like 2x plus 4y minus 3z. This is what it is. Now if this is equals to 0, Okay, just a minute. I just want to know. Okay, is there any shortest method? I mean, this can be done, but there's whether there is any shortest method that I just wanted to obtain. Okay, let's see still what happens. So I need the orthogonal projection. So let's find what is x, y, z such that t minus 2y x, y, z it is. Okay, this is equals to 0. So this will be equals to the all those x, y, z for which this 2x, this matrix things happens. Okay, so then what is the solution of this fact? But can I give it directly? Any direct solution? This is eigenvalue. This is eigenspace. Okay. No. Okay. Sorry. I don't need this fact also. I don't need this fact also. I can do. I can do without going this. Yeah, this is what I am looking for actually. So there is a formula also. We can obtain this EI also in another formula. This EI also it is, if you recall that this EI is actually equals to the polynomial, that is the characteristic polynomial, minimal polynomial, whatever. This is same thing. So it can write the minimal polynomial MIT by MT by, I mean not MT basically, MX by X minus CI whole T. That means it is actually x minus 5. For example, if I consider the eigenvalue I equals to 2, eigenvalues are 2, 5 minus 5. Is this the order? 5 to 5. So if I consider the eigenvalue 5, then if lambda 1 is equals to 5, this gives me that E1 is equals to x plus 5 and x plus 2, x plus x minus 2. So this is going to be like t minus at the point t. This is going to be like t minus 2y whole into t plus 5y. So now what is EI? E1, this is E1. E1 maps xyz. What it will map? It will map t minus 2y of t plus 5y and x plus y plus z. Sorry, x comma y comma z. So where t is actually mapping t minus 2y, let's keep this one, and I don't know why this becoming very bizarre. Okay, t plus 5y, that is 5y going to be like xyz, and t is going to be t will map there is a big map. Problem is that there's that big map. What is that big map? Mm, t, yeah, that 4x minus y minus z comma x minus y. So this will be minus 5x, so plus 5x comma minus x minus y plus 4z plus 5y comma minus x plus 4y minus z plus 5z. This is what it is. So this will be like t minus 2y. This will be like 4x 5x 9x minus y minus z comma minus x plus 4y 4z comma this will be minus x plus 4y minus 4z. But why one terms is going to be different? Okay, so now what it will be, t of this one will be 4 times 9x minus y minus z minus x plus 4x minus y minus z. Okay, this is the calculation only, and minus this is minus times minus x plus 4y minus 4z minus 2 times 9x minus y minus z. Yeah, 2 times x. Yeah. So this is the first entry. So second entry is minus 9x minus y minus z minus of xy, that is minus x plus 4y plus 4z plus 4 times z, that is minus x plus 4y minus 4z minus of 2 times the second entry, that minus x plus 4y plus 4z. This is the second entry. And third entry is minus x plus 4 times second entry, x plus 4y plus 4z minus z times last entry, yeah, minus z, that is the last entry. Last entry is actually minus x plus 4y minus 4z minus 2 times the z, that is minus x plus 4y minus 4z. Okay, I don't know what it is, so let me check, just calculate the first one. So if we try to find simplify this, you can look at carefully that first one will be 2 times 9x, that is 18x. This is plus x, this is plus x, that is 20x. This is not going to match. Just a minute. Whether am I doing EI little different? I think I have. We have done this type of problem earlier also, but I'm doing mistake. I think we have done this type. I think I'm doing little mistake. So let me just give me 2 minutes, 1 minute. T is diagonalizable. Then what will be EI? This expression has a little problem. If I have T is equals to E1, C1, C2, E2 plus C3, E3. So P minus C1I identity, that has to be equals to E1 plus E2 plus E3, that's going to be 0. So I think that is actually linear combination of, that's not product actually. I think that's not product. Okay, so let me give 1 minute. I have done these problems in above also. Just give me 1 minute. I think I have done this type of things already. Ah, this one. EI actually equals to this one, that x minus c1, x minus c2, x minus ck by c1 minus this, c1 minus this. But okay, there will be a factorization. That will be like c1 minus c2. That has to be there, but still there. This is not going to be 0. That's the problem. Here it is. Yeah, here it is. If I is equals to this, okay. From this is the technique I want to use. This one. So t minus 6I is equals to this one. So I'm using correctly, but problem is that this has to, we have to do the calculation only. So there has to be c1 minus c2 only. That x minus, if you have the x1, x2, these are the three eigenvalue, x1, 2, 5 and all those. Okay, let me go there. And I'm doing correctly, but calculations is a little lengthy. Okay, let me. Yeah, here it is. So here actually thing is that e1 will be 1 by, so this will be like x minus e1 will be like x minus c1, that is x minus c2, x minus c3 by c1 minus c2 and c1 minus c3 at the point t. So here c1 c2 cn, that is equals to c1 is equals to 5, c2 is equals to 2 and c3 is equals to minus 5. So in that way c1 is equals to 5. If it is a c1 minus c2, that is equals to 3, and c1 minus c3, that is equals to 5 plus 5, 10. So that is 30, right? C1 minus C2, that is 2, that is 3, and C1 minus C3, that is 10. So that is 1 by 30 it will be. 1 by 30 multiplication will be there. 1 by 30 multiplication will be there. And then here it will also be 1 by 30 multiplication. So what is the first entry actually coming? That first entry is coming like minus 2x minus, this will be like 2 times 9x, that is 18x. 18x plus x, that is 20x. Okay, let me calculate this. And this is 4y. What is the coefficient of y? That is 2 minus 2y minus 4y minus 6y minus 4y minus 8y. And minus 4z, that is 2z minus 4z minus minus plus 4z, that is minus 2z. I don't know why it is not matching. Just let me see. But at least it is matching or not, that by 30, right? That by 30, that is, at least is it matching with at least one or not? 30 means yes, it is actually matching. No, 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 no. Minus 4z, minus 4z, 8z. Oh, okay, just a minute. Five x. There is a mistake. This is plus 4z. This is plus 4z. This is plus 4z. This is plus 4z. Yeah. So now it will be this will be 2y minus 4, 4, 8y, 8y minus 2y, 10y. Okay, this is also mistake. Okay, so this will be minus 2y and minus 4y, 6y, minus this is minus 10y. Yeah, this is correctly. I'm doing correctly. Okay, just wait. Minus 4z, minus 4, minus 2z, then it will be minus 4z, minus 4z, 8z, 8z minus 2z, that is 6z. But this is going to be minus 2z, minus 4z, minus that is 10z, minus 10z. This is the first entry, and the second entry is that. So this will be like 9 minus 9x. This will be minus 3. So basically, I can cancel out this one. So minus 9x plus x plus 3x, that will be minus 6x. Yeah, 3x, 6x. With plus y, minus 4y, minus 3y, minus 12y plus 16, that is 4y plus y, 5y, and z, that is plus z, minus 4z, minus 12z, 16z, that is 4z plus z plus 5z by 30. And another is, it's actually matching. Another is last entry. So if we do calculation, so here it will ultimately, okay, let me give you the answer. So this will be equals to 4x minus 10y minus 10. Here it will be like 5y, 5z, and this will be 10. I think I have done mistake. This will be supposed to be 10x, and this is supposed to be minus 2x plus y plus z by 6. I have to check. So this is going to be like 4x minus 2y minus 2z by 6, comma minus for 2x plus y plus z by 6, and this is going to be minus 2x plus y plus z by 6. So this is the one of the option to check, but I don't know any other easy option is there or not. Okay, so this way actually you have to check other two options. I'm not doing here because that will take full class time. Check other two options. So answer is B actually. This is going to be answer. So okay, I have not completed yet, so I'm going to the next problem now. And if I get time, then I'll start to do that. Okay, let's go into the next problem. So, okay, this will be the last problem then, because this is also a big problem. So what it is given here, it is given, consider a matrix A and the singular value decomposition of A represented by U, B, V transpose, where U and V are orthogonal matrices of order 2 and 3 respectively. Then the matrix D is, what the matrix D you have to find. So what is the singular value decomposition? Singular value decomposition is that whenever you have a matrix A, that can be any type of matrix, that 2, 3, minus 2, like this. So this is the matrix. Then what is the A star? A star, here it is actually a transpose, that is 3, 2, 2, 2, 3, minus 2. So if you consider A star A, that will be like 3, 2, 2, 2, 3, minus 2, and 3, 2, 2, 2, 3, 2. Then what we can obtain here, if we just do the calculation, this is like 3 times 3, 9 plus 4, 2, 4, 9 plus 4, that is 13. Next is that 3 to 6 plus 6, that is 12. Next is 3 to 6 plus 4, that is 10. Next is 2, 3, 6 plus 6, 12, that is 2 to 4 plus 9, 13, that is 4 plus 6, 10. The next one will be like 2, 3, 6 minus 4, that is 2. Next one is that, I hope I'm writing correctly, 2 to 4 minus 6, that is minus 2. Next one is a 2 to 4 minus 4, that is 0. This is the matrix. Now it is known that now that A star A is actually is um, is actually self-adjoint and positive definite, positive semi-definite actually, positive semi-definite. What is mean by positive semi-definite? Self-adjoint you can check for any matrix or any operator t star or t star t, they are self-adjoint always. You can check that very easily. Okay, you just do the formula. You just need to use the formula that t1 plus t1 t2 whole star is equals to t2 star t1 star. Use this formula, you will get that A star is actually self-adjoint. Now, what is mean by positive semi-definite? A matrix D or C is said to be self-adjoint. Square matrix. Sorry, is said to be positive semi-definite if C of x comma x inner product that has to be equals to 0. That means x star Cx as a matrix. X star is the conjugate transpose. That is positive. Sorry, that is positive. Greater than equals to 0. That is greater than equals to 0. This is positive semi-definite. And a positive semi-definite matrix for a positive semi-definite matrix eigenvalues are non-negative real number. So why this is real number? Because this is self-adjoint, so therefore its eigenvalues has to be real. First point. Second point, this is a positive semi-definite, so one can check that it has the all the eigenvalues are real, positive. Why? If a matrix C is positive semi-definite, then if lambda is an eigenvalue of the matrix C, then there exists a vector x not equals to 0 such that Cx equals to lambda x. Now I want to prove that lambda is positive. Okay, this is what it is I have to prove. So now note that Cx comma x, that can be written as lambda x comma x, that can be written as lambda inner product x comma x due to linearity. Now this is greater than equals to 0. Now we know inner product x that is greater than equals to 0 if x is not equals to 0, but here we have considered x is not equals to 0, therefore inner product x has to be 0. But if this product, that lambda with inner product x is that greater than 0, that implies that lambda has to be greater than equals to 0, either 0 or it has to be positive. So therefore for any, this is what it is proving here basically, for any positive semi-definite matrix or operators, the eigenvalues, if that exists, eigenvalues has to be positive always. Okay, so here this operator is self-adjoint, but this fact is not needed. I want to obtain its eigenvalues. So what are the eigenvalues? Eigenvalues of A star A is actually equals to 13, 12, 13. I just want to check once again, because if this is wrong, then this problem also going to start here. So A star is equals to, that is bar 3, 2, 2, 2, 3 minus 2, 3, 2, 2, 2, 3. I know there is a mistake always. That's what happened with me. 3, 2, 2, 2, 3 minus 2, 3, 2, 2, 2, 3 minus 2. Yeah, there is a mistake. So I have to check it once again. 3, 2, 13, 3, 3, 9 plus 4, 13, 3 to 6 plus 6, 12, 3 to 6, 3 to 6 minus 4, that is 2, 2, 3, 6 plus 6, 12, 2 to 4 plus 9, 13, 2 to 4 minus 6, 4 minus 6, that is minus 2. Next is 2, 3, 6 minus 4, that is 6 minus 4, that is 2. That is 2 to 4 minus 6, that is minus 2, that is 0. Okay, this is actually symmetric matrix. Symmetric matrix, yes. So the matrix is actually, right now, I have made a mistake, so that's why it is changed to 2 minus 2. Yeah, 13, 2, 12, 2, 2, 13 minus 2, and 2 minus 2, 2. So a star a. So now if I consider x 0 0 0 x 0 0 0 x, that one minus 13 12 2 12 13 minus 2 12 minus 2 0, then this determinant if I want to obtain, that will be equals to determinant of x minus 13 minus 12 minus 2 minus 12 x minus 13 minus plus 2, this will be minus 12 minus minus plus 2 x. This is what it is, I think. Yeah, this is correct. Determinant of this. Now determinant of this is going to be, I have to calculate this determinant. Determinant is going to be x minus 13 into x square minus 13x plus minus 4 minus minus 12, that will be minus 12x, plus plus 24. Next one will going to be minus 2, and this will be like minus 24, and minus minus plus 12x minus 13. Why everything is going to be so bizarre? X minus 13, x square minus 13x minus 4, that's correct. Next is minus minus plus, that is minus 12x, that's correct. That is 24 minus, that is plus. So this is going to be minus 2 and minus 24, that's okay. Minus 12x minus 12x minus 13. So this is going to be like x minus 13 into x square minus 13x minus 4 plus 12. If I take common, then 12 into 12, 144, right? 144, this will be like 2 minus x. This will be like, if I take 12 common, then this will be minus 12 common. If I take, then this will be like 144. Then it will be like x minus 13 minus I have taken. So plus 2, x minus 11. So here I will not do the calculations because this is going to be problematic, I think. So I hope 530 is the eigenvalue. I hope. Let me check, or at least replace 0. If I replace 0 here, then this will be 13 into minus 4 and 144 into 2a2. In singular value decomposition, I have to find A star A and find the eigenvalues of A. So from here, one can neither row sum is matching, neither column sum is matching. Okay, so it will have the eigenvalues actually 25, 9, 0. This is the eigenvalues. Okay, so let me check whether these are the eigenvalues or not. I will not. If I replace 0 here, let me calculate it just using calculators. If I replace 0 here, then there will be like 13 into minus 4 plus 1442 plus 144 into minus 11. So I'm just replacing x equals to 0 here. So this will be like 13 times 4 plus plus 144 times 2 minus 11 times 144. But this is not going to be 0. Did I make any mistake here? Okay, there is an other way. So let's going through that alternative way. I hope that will be. So we have considered there a star a. So here I will consider a star. Okay, a star is equals to a star is equals to what will happen. A was 3 2 2 2 3 minus 2. So a was like 2 3 3 2 2 2 2 3 minus 2, and that will be like 3 2 2 2 3 minus 2. If I do, then this will be a little smaller matrix. So here I think it is possible to do 3 3 4 9 9 plus 4 13 13 plus 17, and this will be like 3 2 6 plus 6 12 minus 4. That is actually 12 minus 3 to 6 to 3 to 6 plus 3 to 6 6 is 12 minus 4, that is 8, and this will be like 2 3 6 plus 6 minus 4, that is 8, and this is 2 to 4 plus 9 plus, that is 17. So this is the matrix. Now what are the eigenvalues? Eigenvalues here it is clear, I think. So now if I consider the eigenvalues of one of the eigenvalues of, if x minus 17 minus 8 x minus 17, if I took determinant of this is going to be like x minus 17 square plus minus 64 minus 8 square. So you can write it as x minus 17 minus 8, and another is that x minus 17 plus 8. This is going to be x minus 25, and this is going to be x minus 9. So basically here the eigenvalues of A stars are 25 9, and that has to be positive because the similar purpose A star is also positive semi-definite. So 25 into 9, 25 and 9. Then this is a general theorem, it is here, it is there. Whatever, I mean, suppose the singular value decomposition of the matrix A is U D V transpose here because it is in real situation. If it is in complex situation, it has to be adjoint. Then then D has to be equals to diagonal of square root of eigenvalues, if lambda 1 lambda 2 eigenvalue, and if lambda 1 lambda 2 lambda 3 are eigenvalues, lambda 1 lambda 2 are eigenvalues, lambda are eigenvalues of the matrix A star or A star A, then D has to be equals to diagonal of square root of lambda 1, square root of lambda 2, square root of lambda r, and to fill it whatever the 0 needed. This is what it is. So here we have exactly same thing. So therefore the matrix D actually equals to, the matrix D has to be equals to diagonal of 5 and 3. So let's see which option it is there. 5 3 and 0, whatever that is, but which matrix? So these are the two possible options, but there will be some order things. Okay, let me check which order is there. So here A is actually 3 by 2 2 by 3 matrix, 2 by 3 matrix. So U has to be equals to 2 by 2 matrix, and V has to be equals to 3 by 3 matrix. So D has to be equals to 2 by 3 matrix. So whenever D is 2 by 3 matrix, so this is the option, so this is not correct. Okay, this is the options, and these two are automatically incorrect. So this is the options. So I am not doing here full. Actually, if you do the singular value decomposition, thing is that if you start with, even if you start with the A star A, and if you obtain the eigenvalues of all the eigenvalues of that operator A star A, then take the square root and take the appropriate diagonal matrix, and that will be the corresponding diagonal matrix inside this. But U and V need some work to do. If you want to know what is U and V, you need to some work to do. Okay, so I will not continue anymore. So okay, once again there will be another tutorial session in the next Monday, 13 April, and that will be the last tutorial session for this course. and there will not be any other tutorial session. So if you have any other doubt regarding this course, any problem, you just can send a mail to this email ID ma21d018 at the rate of smail smail.iit.in .iitm.ac.in. So I'm also writing in the chat section that mail ID ma21d018@smail.iitm.ac.in. If you can send a mail to here, if you have any doubt that problem, you can send a mail to there. So do you have any doubt here? I know I have made many many absurd things today, but if you have any doubt, let me know. Otherwise, I'll stop in few seconds.